Here is just a few quick notes on using the Nernst equation. These are a little bit messy. I just wrote them up and ran them off, but it'll give you an idea of how this equation is used. As it says in your notes, the object of this equation is to calculate the cell voltage if you have non-standard conditions. Most standard conditions means, remember, that solutions are assumed to be 1 molarity solutions. That's really the main thing you normally have to deal with. If you have molarities that are not 1 molarity, that means that the voltages will not be what you find on the chart, so they have to be recalculated. Here on this side of the screen, this is the sort of the original version of the Nernst equation. The new voltage that you're trying to calculate equals the old voltage minus these constants times Q. As we said, they substitute for R and F. Temperature is never anything other than 25 degrees. Natural log ln becomes base 10 log log, which means you end up with an equation something like this one that's given on the AP test. The only thing you have to know how to plug in is N, which is the number of electrons that are involved in either the oxidation or the reduction. And you also have to know that Q is just like when we're doing equilibrium problems, Q is the same kind of ratio, products over reactants. So here's an example. Let's say we wanted to deal with an aluminum and zinc cell, oxidation of aluminum, reduction of zinc. But we want to make the concentrations different than standard. We want concentration of aluminum to be 0.25, concentration of zinc to be 0.1. I have this completely worked out here on the screen. You can certainly pause if you want to copy down all the work, but notice the first thing we have to do is calculate the standard voltage for this situation. We look up the voltages for oxidation of aluminum and reduction of zinc. Remember the little detail that although we multiply these equations so we can cancel the electrons, the cell voltages are not multiplied. This means that our standard voltage for this combination is 0.9 volts. Here's what it looks like as we begin to plug into the Nernst equation. This is the original standard voltage for the cell. Notice that I've used a value of 6 here because back up at the top I would have multiplied both of these equations to have 6 electrons, and that's where I get my value of 6. Here's the products over reactants. My aluminum ion is a product ion, my zinc is a reactant, and I also use the coefficients as exponents. So you plug in the information here for our concentrations, do all your math, and you come up with a new voltage of 0.898. That's not a very dramatic decrease, but it is a slight decrease compared to the standard voltage. It's pretty typical, actually, that these voltage changes are not really dramatic. So that's an example of how to do a problem. There's a couple more that I recommended to take a look at in your book. You can actually generalize a little bit, and I'm sorry, this is kind of hard to read, but sometimes they're asked questions about what will happen to a voltage if you increase or decrease a concentration compared to standard. And very similar to Le Chatelier's principle, you can make some generalizations here. Once again, this is our formula for the Nernst equation. Remember that Q is a ratio of products over reactants. At standard conditions, everything that you would plug into this ratio would have a value of 1. All the solutions would be 1 molarity. And so at standard conditions, this ratio is kind of automatically equal to 1. So what you always have to think about if you change the molarities of your solutions is what is your new ratio going to be? Is it going to be greater or less than 1, which is the ratio for standard conditions? Well, if the product concentrations are greater than 1 molarity, or the reactant concentrations are less than 1 molarity, if you do either or both of those things, then you set up a situation where the ratio Q is going to be greater than 1, right? I'm going to have large numbers on the top, small numbers on the bottom. I'll have a Q value greater than 1. Take the log of that number, work everything out. This whole term in blue brackets will be a positive number of some sort, which means you're going to be subtracting from the standard voltage. Therefore, the new voltage is going to be less than the standard voltage. This is a generalization. If you make the product concentrations greater than 1, or if you make the reactant concentrations less than 1, your ratio Q is always greater than 1, and that will result in a lower voltage, a voltage that's lower than the standard voltage. In terms of Le Chatelier's principle, if we know that if the Q is greater than K, the equilibrium constant, we know that that suggests a reverse reaction. This is a kind of a similar situation. We're having a ratio that's greater than the standard 1 value. And that means that the reaction has some kind of tendency to want to go in the reverse direction. Well, if it wants to go in the reverse direction, then the potential for the forward reaction is less than standard. So that's kind of an alternate way to think about these questions. You can answer them mathematically or in terms of Le Chatelier. Here's the exact opposite situation. What if you make the product concentrations less than 1 molarity and or you make the reactant concentrations greater than 1 molarity? If you plug that in, you're going to have a ratio Q that's now less than 1. And therefore, this term, when you take the log of that kind of a number, it's a negative value. This whole term in blue brackets will be negative, so I subtract the negative, and the overall result is I will have a larger voltage than standard. The cell voltage will be greater than standard, just based on the mathematics of all that. Again, to use a little bit more of a Le Chatelier's type of argument, if your Q ratio is less than K, in this case we're kind of using 1 as in the place of K, because at standard conditions this Q ratio is 1. Anyway, Le Chatelier says if Q is less than what it's supposed to be, this suggests a forward reaction. And so here, that's kind of what we've got going on. Our ratio is less than 1, less than what it's supposed to be at standard conditions. And that means that the reaction has a greater tendency to go forward. Its potential is therefore larger. So that's a way that you can kind of generalize this. The last point to make about these equations, if we I've just written kind of an overall generic oxidation reduction reaction. We know that they typically look like this, where we start with one metal in a solid form and the dissolved form of a different metal, and we end up with the solid Y and the dissolved M. Let's say that this is just some generalized spontaneous redox reaction, so it has a voltage that's positive, greater than 0. When we first set everything up and let it start working, if it's a standard cell, that means that the concentrations of these two ions are going to be exactly 1 molarity. But as we know, that's going to start changing as soon as things start happening. As soon as things start happening, your Y2 concentration will begin to decrease, and the M2 concentration will begin to increase, just because this is going to start happening. If I switch over here quickly, this is that animation that we've looked at several times with zinc and copper. Just to go back and remind you, this is the zinc and copper combination where copper 2+ is getting reduced, zinc is getting oxidized. And as copper 2+ gets reduced, that means that the amount of copper 2+ in solution is decreasing, just by definition of what's happening. Over here on the other side, we know that our zinc metal is corroding away, but notice that that's increasing the amount of zinc that's in the solution. So in general, it's true that once your reaction starts to happen, you automatically start to lose your Y2 substance and increase your M2 substance. This ratio Q, which is products over reactants, remember, so it would be M2+ over Y2+. Automatically, as these cells start to operate, these concentrations change and the ratio Q automatically becomes larger and larger and larger. And remember, as the Q ratio becomes larger, that causes the voltage to decrease. So the result is that a normal situation is that these reactions begin to happen, the concentrations begin to change, and while they're working, the voltage is sort of slowly decreasing as things happen. I'm not sure if our animation here on this page is actually good enough to show that. I know that it shows the changes that we see in the two pieces of metal. If this was an excellent animation, it might run for 20 minutes or something like that, and we could begin to see this little voltage needle go down. But even though it's not going to really do that, that's what would happen in reality. If we let this go for a long enough time, the voltage of the cell would get smaller and smaller and smaller till eventually it would become zero. And that would happen when all of the substances on both sides of the picture are at their equilibrium values. So if you reach that point, like we looked at in class today, the Nernst equation would look something like this. The cell voltage is now 0, and the Q has turned into K because we were at equilibrium. If you do a little math to rearrange this, that creates one of the formulas that we talked about that's given on the AP, the relationship between the equilibrium constant and the standard cell voltage. This is a given equation on the AP test. It actually comes from the Nernst equation. So that's just a little bit about Nernst.